All right, we're moving into chapter 6, which is a chapter on polynomials. But here in the first section, before we can talk about polynomials, we have to look at monomials to start. All right, so we're going to define what it means to be a monomial, how to find the degree of a monomial, and then we're going to be looking at some properties of exponents that can be used to simplify some monomial expressions. Okay, so a monomial is defined to be an expression that's a number, a variable, or the product of a number and one or more variables. Okay. It cannot contain variables that have negative exponents or variables underneath radicals. And you want to think the root word here is mono, which means singular. So a monomial, it has to be a single term. It can't have multiple terms to it. All right. So examples of monomials, 3 is a monomial because it's just a regular number. 5x is the product of a number and a variable, so it's a monomial. X cubed is the same as x times x times x, so that's the product of a variable multiple times. And then 4x squared y, that's a monomial because it's just a product of a number and multiple variables. Non-examples, x plus 8, that's not considered a monomial. It's instead a binomial because it has 2 terms to it. X and 8 are separate terms because of the addition between them. Square root of x is not a monomial because of the radical. And then x to the negative third is not a monomial because of the negative exponent. Okay. Now, every monomial has a degree associated with it. And this is nothing more than the sum of the exponents of the variables. So of course, sum implies addition, right? We have to add the exponents on all the variables up to find the degree. If your monomial is a non-zero constant, then it has a degree of 0. And the number 0 itself, it's kind of its own special case. 0 has no degree, all right? So the monomial of 2x, I would say that has a degree of 1. That's because the power on the variable x is 1. Okay. 6x squared y cubed, that has a degree of 5 if you add the powers of 2 and 3 together. 5xy has a degree of 2 because the powers on both variables are 1. Adding them up will give you 2. 2, that's a non-zero constant, so it has a degree of 0. And then 0, 0x, 0xy. Don't all of those actually simplify to the number 0 itself? We would say that all of those monomials have no degree. Okay? All right, now let's look at some properties of exponents that can be used to perform some different operations on our monomials, right? These properties are probably not new to you. The new concept would be thinking of them in terms of monomials, utilizing them with operations on monomials, okay? So let's say I have a monomial of x to the power of a multiplied by a second monomial of x to the power of b. The fact that both monomials have a base of x allows me to add their exponents together and say that this equals x to the power of a plus b. All right, so I'll give you a quick little example on that. We're saying that if I was multiplying x squared with x cubed, then that's going to equal x times x, right? Multiplied by x times x times x. So altogether, you have x being multiplied 5 times here, which we know is x to the 5th power. All right, so of course you've got the shortcut using this property. Simply add the 2 and the 3 together to give you that power of 5. All right. X to the power of a, if you divide that by x to the power of b, you're going to equal that to x to the power of a minus b. So that shows me I am subtracting the power from the numerator by the power of the denominator. Okay, so example for that, let's say we're working with x to the fifth divided by x to the second. So of course, x to the fifth is x times x times x times x times x, right? And x to the second is simply x times x. Well, you can do some reducing here. Can wipe out a couple pairs of x there, and notice what you're left with. X cubed up in the numerator, and then just a 1 in the denominator. So this, of course, equals x cubed. All right, so of course, the shortcut using the property is to get that power of 3, just subtract 5 by 2. All right. If I take a monomial of x to the power of a and I raise it to another power of b, then I can simply multiply the two powers together, x to the power of ab. All right, example for that. If I was working with x squared and I try to cube that, we'll understand that that means you're taking x squared multiplied by x squared multiplied by x squared, okay? And once you think of it like that, you can use the property above, that product property, and you could add the exponents all together. 2 plus 2 plus 2 gives you x to the sixth. All right, so of course, the powers of 2 and 3 multiply together to give you that 6 as a shortcut. Okay. Let's say my monomial is made up of multiple pieces. So I have x times y as my monomial, and I raise it to a power of a, then technically both x and y should be raised to that power. Okay. An example where this often gets misapplied, let's say my monomial is 2x, and I'm raising it to the third power. So that means 2x times 2x times 2x, right? Well, notice you'd be multiplying 2 a total of 3 times, so that's 2 cubed, and also x cubed, which gives you 8x cubed. All right, so notice the shortcut is just take 2 and cube it, take x and cube it to get to your simplified expression. All right. Okay, what about x to the 0 power, right? Anything to the 0 power is actually defined to equal 1, all right? Now, an example of this, or a proof, I guess I'd say, is actually based off of the quotient property. All right, so let's say I'm working with x to the power of m over x to the power of m, all right? Well, we know that if you divide something by itself, it equals 1, right? So in the end, I know this is going to equal 1, but understand if I apply the quotient property of exponents, that means I would subtract the numerator's exponent by the denominator's exponent, and wouldn't that just lead me to x to the 0 power? And of course, we can then say, well, we knew from the get-go that anything divided by itself equals 1, so that must mean x to the 0 power equals 1 as well. All right? What if you raise a monomial to a negative exponent? Well, this is, if I have x to the power of negative n, that's the same as 1 over x to the power of positive n. All right? So an example of that, let's say we're working with x to the negative second power. That's nothing more than 1 over x to the positive second power. Okay. Now, what if I was working with something like 1 over x to the negative third, where the negative exponent's in the denominator? Well, this is now just going to equal x to the positive third, where that's over 1. It now becomes in the numerator. So don't overcomplicate that property. Basically what it's stating if you have a negative exponent, you can turn it positive by simply putting it in the opposite side of the fraction. Okay? All right, some examples to utilize these various properties, okay? Think of these problems as nothing more than operations on monomials where you have to apply these properties of exponents, okay? So negative 2a cubed b, that's a monomial that's multiplying negative 5ab to the fourth, okay? You're going to multiply the like parts together, all right? And in the process, you'll use your product property of exponents. So negative 2 and negative 5 are your coefficients. They're going to multiply to 10. A cubed and a, if you multiply those together, you'll end up with a to the fourth by adding their exponents. And b times b to the fourth would actually be b to the fifth by adding their exponents. Okay. All right, s squared, if you divide that by s to the 10th, you could subtract the exponent, do 2 minus 10, and that'll give you s to the negative 8th. We don't want to leave the exponent as negative, though, so we're going to write this as 1 over s to the positive 8th. Okay. All right, and then for c, we just have 3 monomials being multiplied together. We're going to start off approaching this like we did the problem directly above it. We're going to multiply all the like parts together. So my coefficients are 3 and negative 2. Those will multiply, of course, to negative 6. A to the fifth multiplied with a to the negative fourth. If you add 5 and negative 4, you'll end up with a power of 1 on a. So that's just a to the first power. And then you only have one expression that has b cubed in it, so just carry that down. And then the same with c to the negative second. Okay. Now, that's not completely simplified because notice you still have a negative exponent on c. So this will become negative 6ab cubed over c to the positive second power. Notice I only placed c down in the denominator because it was the only part that had exponent that was negative. Okay. All right, some more examples. These are a little more sophisticated. In part A there, we have a monomial that's being raised to a power. So this would involve your power to a power rule. Each piece of the monomial needs cubed. So negative 3, if I cube that, that'll give me negative 27. C squared, if I cube that, I'll multiply 2 and 3 together to give me c to the 6th. And then d to the 5th, if I cube that, that'll give me d to the 15th. Okay? That's as simplified as you can get. All right, negative 2a over b squared. If you're raising that fraction to the fourth power, we know that both the numerator and the denominator have to be raised to the fourth, okay? So negative 2, if I raise that to the fourth, it'll give me 16. A raised to the fourth would be just a to the fourth. And then b squared, if you raise that to the fourth, you're going to multiply your exponents to give you b to the 8th. Okay? And then you can't do anything to simplify the numerator with the denominator there. All right, next, negative 3a to the power of 5y divided by a to the power of 6y times b to the fourth. We're raising that whole fraction to the fifth power. Now, what I'm noticing on the fraction itself is you can actually simplify a to the power of 5y divided by a to the power of 6y. If you subtract 5y by 6y, you'll end up with negative y on the power of a. To make that positive, you'll just put it down in the denominator. So this becomes negative 3 over a to the power of y times b to the fourth. And then that's all still raised to the fifth. Okay. Now raise every part of the numerator and denominator to the fifth power. So negative 3 to the fifth power is negative 243. A to the power of y, if you raise that to the fifth power, multiply 5 and y together, it'll give you a to the power of 5y. And then b to the fourth, if you raise that to the fifth power, you'll end up with b to the 20th, as simplified as we can get. Okay. All right, now a bit of an application to our monomials and specifically our properties of exponents, okay? It involves scientific notation. And just recall, you've probably worked with scientific notation before. In order for a number to be written in scientific notation, it's going to follow the format of a times 10 to the power of n, where a is a number between 1 and 10, and n, the power on 10, it's got to be an integer, okay? So if I am working with two numbers in scientific notation, I can utilize my properties of exponents on those, okay? So let's say I'm taking 1.5 times 10 to the second power, and I'm multiplying that by 2 times 10 to the fourth power. Well, I can simply multiply 1.5 and 2 together. That's going to give me 3. And then here's where the property of exponents comes into play. 10 to the second, if you multiply that by 10 to the fourth, add their exponents, that's going to give you 10 to the sixth. Okay, and notice that number, that result is still in true scientific notation. Okay, works the same for division. If I'm taking 4.2 times 10 to the sixth divided by 2 times 10 to the third, 4.2 divided by 2 gives you 2.1, and then 10 to the sixth divided by 10 to the third, you're going to subtract your exponents here, and that's going to give you 10 to the third. Okay, notice again the result is still in true scientific notation. Okay, all right, now notice the final example here, we are adding our numbers together. All right, in order to add or to subtract in scientific notation, your exponents on the power of 10, they have to be equal to each other. Okay, so right now in this example, I have 10 to the second power and 10 to the third power. So that means these numbers aren't to the same place value right now. So I need to change that. All right, so I'm going to leave the first number the same. And then if I want to change 1.3 times 10 to the third so that 10 is being raised to the second power, if I'm going to reduce the power, I need to increase the value of 1.3. So it's going to become 13 times 10 to the second. Okay, 13 times 10 to the second is equivalent to 1.3 times 10 to the third. Now I can add 2.1 with 13. That's going to, of course, give me 15.1. And I simply copy down 10 to the second. Okay, I don't actually do anything with the powers on 10 there. Now notice this result is not in true scientific notation. Why? Because 15.1 is not between 1 and 10. So, of course, to make it between 1 and 10, I need to move my decimal place over to the left one spot. This becomes 1.51. So effectively 15.1 is reducing, it's becoming smaller by turning into 1.51, which means my power needs to increase to 3. Okay, so now I'm in true scientific notation. So that's just something to watch out for when you're working with these numbers. Make sure the result finishes in true scientific notation.